Hello everybody, welcome into the very first lesson of Calculus 1. Today we are going to introduce the idea of a limit. So what is a limit? Well, you may see this notation here, lim x arrow a, f of x equals L. So what does that mean? The idea is of a limit. That's how you abbreviate a limit. The idea is, as x approaches some number, which in this case we'll just say some generic number a, what value does your y value approach? In other words, what value does the function at that value of x approach? It's going to be some generic number L. That's just the generic notation. So as x approaches some number, what value does your function approach, or what value does y approach? And one very specific way of doing this is graphically. So we'll do a few graphic examples of how to evaluate a limit. So I'll start out real easy. Let's do f of x equals x. So I'm going to evaluate a limit for this function. We'll take f of x equals x, a classic line. So let me just go ahead, plot some points. We'll draw a nice line here. Alright, so let's go up here. Alright, I think we get the idea of that line. And why don't we do the limit as x approaches 3 of x? Why don't we do that? So we want to know the limit as x approaches 3 of our function f of x equals x. When you see that x here, that's actually your f of x. The limit as x approaches 3 is the x value of 3. This x is really y equals x. So what value is y approaching? Well, you could think of a limit this way. Let's say you and a friend are walking towards each other. You and your friend are some distance apart. And you're both going to meet at a certain point without actually touching. If you are stopped somewhere, then you slowly start walking towards each other and stop again, you're getting closer to each other, but you haven't touched. Now, if you keep walking towards each other, decreasing the distance by half every time, you'll eventually reach a point where you get infinitely closer to each other without actually touching each other. That's the idea of a limit in the real world. That's one idea, the best way to explain it. If we look at this graph, so limit as x approaches 3 of x. Basically, if I put in 3 for this function, if I put in 3 for my x, I should get a value of 3, shouldn't I? Well, if I go along this curve to the left, I'll draw that in the red ink. I'm getting real close to 3. And then I can also approach from the right. So let's say I'm approaching from the left, my friend is approaching from the right. We'll eventually approach this y value of 3. We do eventually approach 3 there. In fact, why don't I label this point to be at 3, 3. So we will approach a y value of 3. So you can say the limit as x approaches 3 of x equals 3. And you may be thinking, well, isn't this graphical approach a bit overkill? At first, it kind of is. For a problem like this, it kind of is, to be honest. And in a couple lessons from now, we're going to get into limit laws and methods for dealing with limits. And one of them is, if the function is defined at that x value, you can use something called direct substitution and just put in that x value and get your limit. But that doesn't always work, as we're going to see later today. We're going to get into some examples where direct substitution unfortunately does not work. Especially, let's say I gave you something like this: the limit as x approaches 0 of 1 over x. Okay, so if you just put in 0 here, you're going to get an undefined value, right? Sometimes direct substitution doesn't always work. This is why we have to do this the long way. We got to show you what we're looking at here graphically. We're also going to talk about numerically doing this today, but let's do a couple more graphical examples of limits. Alright, this time I think we'll let f of x equal x squared. So we'll draw a parabola. So let's go ahead and draw a nice parabola. Alright, so as you see, you have a nice parabola, f of x equals x squared. Why don't we take the limit as x approaches 2 of x squared? So let's find the limit as x approaches 2 of x squared. Okay, so let's go ahead. As x approaches 2, if I take my x value of 2, let me go from the left here. If I try to go to the x value of 2 from the left along the curve, I'm approaching a y value of 4, right? And the same really if I approach it from the right of x equals 2, I'm approaching a y value of 4. Because here is my ordered pair 2, 4. And since we know this function x squared is defined at x equals 2, we could have used direct substitution to give us a y value of 4. I'm just trying to show you a graphical representation of what we're looking at. So the limit as x approaches 2 of x squared would equal 4. Let's do a trig example. I would like to do one trig example, and then we're going to get into numerical ways of dealing with limits. So let's say f of x equals the cosine of x. So f of x equals the cosine of x. In fact, let me go ahead and graph this. We know at 0 you'll get a y value of 1. Let's make this, we'll call this 2 pi. Here's pi. Here's 3 pi over 2. Here's pi over 2. I just want to label sufficient points. I really like to get a good, accurate graph. Here's negative pi. Negative 3 pi over 2. And then 2 pi. So let's go ahead and graph this. So I know pi over 2 I get a y value of 0. Pi I get negative 1. 3 pi over 2, 0. 2 pi I get 1. Negative pi over 2 I get 0. Negative pi 1. Negative 3 pi over 2, 0. And negative 2 pi I get positive 1. Alright, so let's go ahead and just draw a nice curve from negative 2 pi to pi. Let's say I want to take, and I'll just take the limit as x approaches 0 of the cosine of x. So let's take the limit as x approaches 0 of the cosine of x. So as I approach 0, my x value from either the left or the right, what y value does this function approach? Well, if I approach x equals 0 from the left, notice I'm approaching a y value of 1. And we could argue the same if I approach it from the right. If I approach it from the right, I'm also going towards a y value of 1. So the limit as x approaches 0 of the cosine of x is in fact 1. And we could have even done direct substitution and put in cosine of 0 gives you 1, because cosine is defined at an x value of 0. Or sometimes, yes, you may even see, how about the limit as x approaches pi of the cosine of x? So here's pi. If I approach pi from the left, I'm getting closer and closer to -1. Also, if I approach that x value of pi from the right, I'm getting closer and closer to -1. So the limit as x approaches pi of the cosine of x would be -1. And we could have used direct substitution. Alright, so that actually wasn't so bad when you look at it graphically. Now, let's go ahead and get into some numerical approaches with this. In fact, I'm going to take this graph magnet down, these graph magnets, because what we're about to do is purely numerical. So just bear with me a second. So, okay, up till now we've seen the graphing approach for evaluating limits. Pretty simple, right? Graphing approach is actually pretty easy. Now, there's also numerical ways of dealing with this. So, let's say I give you something like f of x equals the square root of x plus 4 minus 2 all over x. I'm giving you that function, but I would like to know the limit as x approaches 0 of this function. So the limit as x approaches 0 of the square root of x plus 4 minus 2 divided by x. Well, here's the problem. If we just substitute in 0, you'll get a 0 in the denominator, which is undefined, right? That's what's called an indeterminate form. It's undefined. Now, you could graph this, that's true, but it's going to be awful to try to graph. Sometimes you want to make a table of values. So, what you want to do, you want to approach from both the left and right side of this x equals 0. Now, the closer and closer you get to 0 on either side, the better estimate you're going to get. Well, I tell you what, why don't we start when x equals -1? So let's make our table of values here. So let's pick x equals -1. So if I put in -1, what's that going to give me? So I'll take f of -1. Let's solve for that. That's going to, of course, give me the square root of 3 minus 2, all that divided by -1, which could simplify into 2 minus the square root of 3. Well, let's go ahead and get a decimal approximation. Why don't we go to about 4 decimal places just to be safe? You get about 0.2679. So you'll get about 0.2679 if you plug in -1. Alright, now what if I plug in +1? I'm trying to stay the same interval apart. If I plug in positive 1, so let's deal with x equals positive 1 this time. So f of 1, we'll put in, if I put in 1, that would give me the square root of 5 minus 2 divided by 1, which is just simply the square root of 5 minus 2. So let's see what we get. You get approximately 0.2361. So f of x is approximately equal to 0.2361. Well, they're a little far apart still. You want to get these values as close together as possible. So we're previewing about 3 lessons from now where we talk about one-sided limits. In order for the general limit to exist, the right-sided limit, so the limit from the right, must match the limit from the left. You want to get as close as possible for decimal approximations. These are still a little far apart for our liking. So what if I put in negative 0.5? Alright, so I'll take f of negative 0.5. Well, that's going to give me the square root of 3.5 minus 2 all over negative 0.5, which would really give me 2 minus the square root of 3.5 divided by 0.5, and then I could come up with a decimal approximation. So x would equal negative 0.5. Let's figure out about what f of x is going to come up to. So let's see here. If I do this then, so we'll take 2 minus the square root of 3.5. Let's divide that by 0.5. You get approximately 0.2583. So approximately 0.2583 for f of x. Alright, so that's x equals negative 0.5. What if I put in x equals positive 0.5? So notice I'm getting closer and closer to that x equals 0. So that would end up giving me the square root of 4.5 minus 2 divided by 0.5. So let's go ahead and do all that. So f of x, let's take an approximate value here. So let's see. The square root of 4.5 minus 2. Now divide that by 0.5. You get approximately 0.2426. Alright, so we're getting closer and closer together, but I still think we could do a little bit better. What if we pick, let's do negative 0.1. Why don't we pick negative 0.1? So we'll take x equals negative 0.1. Then we could find out about f of x, figure out about where we're going to end up. So that would give you the square root of 3.9 minus 2 all over negative 0.1, which you could simplify as 2 minus the square root of 3.9 divided by 0.1. Let's go ahead now and get ourselves a decimal approximation. Alright, so 2 minus the square root of 3.9, divide that by 0.1, you get approximately 0.2516. And of course, you know what's coming next. Why don't I pick f of positive 0.1? So x will equal positive 0.1. We could get a decimal approximation for f of x. So this would turn into the square root of 4.1 minus 2 all over 0.1. And let's just get decimal approximation for that to 4 decimal places. And let's see, you get the square root of 4.1 minus 2, divide that by 0.1, you get approximately 0.2485. Alright, now we're getting really close. I think we see which way this is going, but what if for the final two numbers, let's pick f of negative 0.001. What if I pick that? So we'll make x equal negative 0.001. Let's take that and find the decimal approximation for f of x. Well, that's going to give me the square root of 3.999 minus 2 divided by negative 0.001, which could simplify as 2 minus the square root of 3.999 divided by 0.001. So now let's take a decimal approximation for that value to 4 decimal places. So 2 minus the square root of 3.999, divide that by 0.001, you get approximately 0.25. To 4 decimal places, you get approximately 0.2500, which is 0.25. And of course, let's pick f of positive 0.001. So if I do that, I'll end up getting the square root of 4.001 minus 2 divided by 0.001. So let's go ahead and plug these in. We can now get a decimal approximation. So let's see here. Square root of 4.001 minus 2. Now divide that by 0.001 to you get to 5 decimal places at 0.24998, which would round to about 0.25. So basically, you could go infinite decimal places. Look how close we get to that x equals 0 on either side. You want to take at least 2 estimates the same length apart on either side. So we started a whole unit apart, got some estimates for the function value. Then we started half a unit apart each from 0 on the left and right. We got some closer estimates to the limit. And then we started only 1/10 of a unit apart on each side of the function value, got even closer. And then we finally went 1/1000th of a unit apart on each side, and we arrived at 0.25. Now you may not always get exact, but if you can see a pattern and which way it's headed on both sides of that x value, you can generally come to a consensus for your limit. So based on the table of values, and we could in theory keep going forever, that's going to equal 0.25, which we know is the same as 1/4. So the limit as x approaches 0 of this function is actually, you could say, either 0.25 or 1/4. And good news is we're not always going to have to do a table of values. One of the ways of evaluating limits we'll get into in a couple of lessons is using the conjugate of the function. So that would have been a way to simplify it, but I'm trying to show you the numerical way right now. So the idea is the closer and closer you get on either side to that x value, the more accurate your limit's going to be. So that's why you might want to start out with a table of values and get infinitely closer until you arrive at a general consensus of what it's going to be. Alright, let's do just one more, okay? I know this part's kind of long, and I warned you in the intro video to this course that it does start out a little boring, so my apologies, but what if I gave you this one? F of x equals the tangent of 3x divided by the tangent of 5x. Alright, so f of x equals the tangent of 3x divided by the tangent of 5x. And I'm going to lay a general disclaimer. In calculus, we deal pretty much exclusively in radians. So don't even think about degrees, really. Just think about radians. We want to take the limit as x approaches 0 of the tangent of 3x divided by the tangent of 5x. Now, we're going to learn some methods for dealing with trig limits a little bit later, and we're even going to, once we learn derivatives, we'll learn a method called L'Hopital's rule that'll help us really shorten the work to find this. But for today, all we have are numerical methods. So the limit as x approaches 0 of the tangent of 3x divided by the tangent of 5x. Well, we can't do direct substitution because you would get tangent of 0 divided by tangent of 0, which gives you 0 over 0. That's an indeterminate form. It's undefined, so that's not going to work. My best advice, again, why don't we come up with a table of values? And to shorten the workload, let's only go 1/10 of a unit apart on each side. So let's take x equals negative 0.1, and we'll go to 4 decimal places again. And then we'll do x equals 0.1, and we can find a decimal approximation there. Okay, so if we take f of negative 0.1, we'll end up getting the tangent of negative 0.3 divided by the tangent of negative 0.5. Well, if we remember tangent's an odd function, this would actually work out to be negative of the tangent of 0.3 divided by negative of the tangent of 0.5. Well, good news is your negatives cancel, so this would just turn into the tangent of 0.3 divided by the tangent of 0.5. And actually this is great because whether we put in plus or minus 0.1, it should work out to be the same, right? Because if I put in just the positive, we would still end up with the positive tangent of 0.3 divided by the positive tangent of 0.5. So we can actually do two of these estimates at once. So that was actually a pretty nice trick. If you remember even and odd functions from pre-calc, that's great, because this is really going to make your life a lot easier. So let's go ahead and do that. Let's take some decimal approximations. Let's make sure we're in radians. Now, let's see, the tangent of 0.3 divided by the tangent of 0.5 gives you approximately 0.5662. And that'll be true for both positive and negative. Alright, well, now why don't we go 100th of a unit apart? So let's take x equals negative 0.01 and x equals positive 0.01. So since we have the odd function property of the tangent function, this is actually going to work out the same for if we put in plus or minus 0.01. And since we've demonstrated that tangent's an odd function, you would get a, if you put in the negative, you'll get a negative in both numerator and denominator. That would cancel out the negative. So let's take f of plus or minus 0.01. Well, that's going to give you the tangent of 0.03 divided by the tangent of 0.05, and then we can get a decimal approximation for those. So let's see what we get here. The tangent of 0.03 divided by the tangent of 0.05 to 4 decimal places gives you pretty much, you get 0.6. So you get approximately 0.6. And if we would like to feel good, why don't we do one more set where we go 1,000th of a unit apart? So we'll take x equals negative 0.001 and x equals positive 0.001. So we can get estimates for both of those at once. Alright, so let's do f of plus and minus 0.001. That would give you the tangent of 0.003 divided by the tangent of 0.005. So we'll put these into our calculator and get some numerical values. So let's take, the tangent of 0.003 divided by the tangent of 0.005, and it rounds to 0.6. So you're getting a consistent 0.6. In fact, if we kept going with more decimal places, that's what you're going to get, is 0.6. So what can we say then? We can say that this limit converges to 0.6, also known as 3/5. So the limit as x approaches 0 of the tangent of 3x divided by the tangent of 5x, you could either say it's 0.6 or 3/5. Alright, so that's it for this lesson. Next lesson we're going to talk about tangent lines and velocity problems. We're actually going to introduce slope a little bit. We're going to talk about slope of lines, especially for nonlinear lines. And we'll use all that. We'll talk about the secant lines, how to get tangent lines, and we'll do some of that for velocity problems a little bit too. So I hope everybody has a great day. Take care.